Hello, Mrs. Van Kralingen and Mr. Leithman. Our Casno project is a collaborative one between me, Eric Fan, Jonathan Cao, and Jonah Chen. For our project, we coded Alex, an artificial intelligence dedicated to predicting stock market prices in C# without using third-party library code dedicated to creating AI. This means that we have to have a good understanding of the mathematics behind how AI works. And we also need massive amount of data in order to train our model. I'm happy to say that our effort did not go to waste and the project ended in complete success. And we will be sharing the result of our project near the end of the presentation. All of us each spent 60 hours on this intensive and rewarding project, and each of our role is crucial to the completion of the project. For this presentation, we'll be going over how AI works, how they train, and the mathematics behind them all. We'll start by introducing neural networks and how they can be represented by mathematical constructs. Then we'll go over gradient descent and backpropagation to explain how AI can make accurate predictions. Finally, we'll talk about how we eventually coded it and obtained a result. First of all, what is AI? AI is an accurate decision-making function that can be represented by a neural network model. What that means is that the AI will take some inputs given to it and produce an output, which is the decision that it eventually made. As seen in the picture, a neural network consists of different layers, where each layer contains different nodes, and every node of one layer is connected to every node in the next layer. The input layer represents the input given to the neural network, and where then it's going to go over some calculation, which I'll explain in a bit, and finally we produce an output. In the most conventional neural network, the nodes in the hidden and output layer are going to consist of numbers between 1 and 0. Since the neural network is inspired by how the human brain works, each node represents a neuron, and the value of the node can represent how active the neuron is. For example, if the neural network is a cat-dog classifier, then it's going to have two nodes in the output layer, where one node will represent cats and the other will represent dogs. If the cat neuron is active, then the neural network predicted that it's a cat, otherwise it's a dog. For our project, the value of the nodes are not going to be between 0 and 1, and I'll explain why soon. So now that we know about the input and output layer, what is happening in the middle with the hidden layers? Well, here's how the math is going to work. Every one of these connections between the nodes represents a number called weights. The values of the nodes in the hidden layer is going to equal to the sum of all the product of the values in the nodes in the previous layer times the respective weight, which then adds to a bias before going through an activation function. This may be better explained using mathematical functions. So the weights, represented by the green letters, represent the connection drawn between the nodes of the previous layer and the node of the current layer, which also represent a number. All of the weights are multiplied by the values of the nodes in the previous layer, and then they are added up together. After that, a bias is added in the end to shift the sum, so that the neural network produces a more accurate result. Note that the weights and biases are different depending on the neurons, and at the very beginning, these values are randomly generated. When we say training a neural network, we mean to change the values of these weights and biases so that it gives us our desired results. Finally, the sum then goes through an activation function. There are different types of activation functions. The most conventional one is the sigmoid function that squishes the value to between 0 and 1, so the value of the neuron will be between that range as well. However, recent studies shows that there are better activation functions that can be used, and for our project, we use the ReLU function. Note that the activation function is used to introduce nonlinearity so that the neural network can predict using nonlinear data, which is data in the real world. The ReLU function will set any negative number as 0, and any positive number will remain the same. For our neural network, we want the network to produce a number that it predicts as the highest value of the stock of the company of that day, which is not between 0 and 1, but also cannot be negative. That's why ReLU is the best function to use in this scenario. In order to properly train the neural network, we must design a way to tell the network how far away it is from the desired result. For this, we need cost function, a function that represents the error of the output. In classification neural networks, the output layer are going to consist of multiple nodes, so the conventional cost function is going to be the average of the error of each of the output nodes. However, since our neural network is a regression neural network and only has one output node, we can just define it as the difference between the output and the desired value squared, then divide by 2, as seen in the picture. Note that the desired value will be the actual highest market value of that day. The reason why we square the differences is so that we can avoid any negative values, since whether the predicted value is below or above the desired value, the error will still be positive. We divide the square by 2 simply because it will have no effect on how the neural network sees the error, but it makes coding and calculation easier for the human brains. To train our neural network, we must change the weights and biases so that the cost function will have a minimal value, meaning that the error will also be small. However, changing different weights is going to have different impact on the final cost function. For our neural network, we had 16 input nodes, 4 hidden layers, and we tested with multiple number of nodes in each hidden layer, with the highest being 64. Note that we used the data from the previous 16 days to make the prediction for the 17th day. That's why we have 16 nodes for the input layer. In the above stated neural network, it will consist of 13,376 weights and 256 biases. And we have to calculate how much each of the weights and biases have to change using gradient descent and backpropagation.
In the process of training the neural network, we must calculate something called a gradient of the cost function. What exactly is a gradient? Before we focus on that, we will first look at a simpler operation called the derivative. Now, many calculus students will learn that the derivative represents, graphically, the slope of the tangent line to a point on the graph. But the actual important part of that which we want is the fact that it gives us both an uphill direction and a steepness. For 2D graphs, as can be seen in the image on the left, a positive derivative would mean that the graph is uphill when moving towards the right, while a negative derivative would mean that's uphill when moving to the left. And the magnitude of the derivative gives us the steepness. Then, we can extend this idea into higher dimensions. This can be seen in the image on the right, which gives an example of the gradient for a 3-dimensional function. The arrows underneath the graph each point in a direction which is in the quote-unquote uphill direction, while the length of the arrow gives the magnitude. For the actual neural network, this is of course very difficult to visualize because our gradient is for much higher dimensional space, with 1 dimension for each weight and bias. Once we are able to calculate a gradient of the cost function, we can then proceed to do something called gradient descent. Since the gradient gives us an uphill direction and steepness, then the negative of the gradient can give us the downhill direction and steepness. And by taking small directions in the direction of this negative of the gradient, we can eventually find a local minimum of the cost, a point where taking small steps in any direction will only increase the cost. In terms of how this is actually applied to the neural network, we calculate this cost gradient by plugging in all of the weights and biases, and the negative of the gradient tells us how much we should adjust each of those parameters in order to reduce the cost as quickly as possible. Then, to make sure we only take a small step, we multiply that negative of the gradient by a smallest number called the learning rate. And then we adjust each of the weights and biases by that adjusted value. Then, this process is applied many times until the cost doesn't change anymore. The actual calculation of the components of the gradient and the adjustment of the weights and biases is done through a process known as backpropagation. Since the values associated with each layer depend on values for layers which come after them, the naive calculation of each component would result in a lot of wasted time. Thus, the calculations are carried out from right to left, with each calculation building upon ones which were done before. This is the idea of the backward propagation of errors. That is, we first calculate the error between the expected output and the actual output, and then this is propagated backward through the neural network, thus the name backpropagation. In calculating the gradient, we apply something known as the chain rule, which allows us to find the necessary change for one component by expressing it in terms of multiple other changes that are easier to find. Listed on the left are some of the required formulas. They may look complicated, but if we set aside all of the complexity as notation, they become easier to understand. Reading from right to left, the first formula essentially states that if we know how much the activation must change for a given change in the cost, how much the input to the activation function must change, given that change in the activation, and how much the weight must change, given that change in the input, then we can find the necessary change in the weight for a given change in the cost. The second and third formulas are similar, but we replace weight with bias and activation. Also, note how the activation formula at the bottom has an extra sum symbol, since the change in a given activation depends on the changes in all of the nodes that it's connected to, and these changes must be added together. While activations cannot be influenced directly, unlike weights and biases, the activation calculation plays an important role in backpropagation, as calculations for previous layers depend on it.
Linear algebra is a powerful mathematical tool used to model systems with many free variables. This tool is used in fields like physics, computer science, chemistry, biology, economics, data science, and a lot more. The effectiveness of this tool is why it is a general institute requirement for most universities. As you have heard previously, our AI model has multiple layers containing multiple nodes each. Each node contains a vector of weights and a bias. Cumulatively, this corresponds to a system with thousands or millions of free parameters that must be optimized via training. Thus, linear algebra is a great model for this neural network, as you will see. We can write the feed-forward procedure, which is initializing the neuron activations from the activations of previous neurons, as the following statement. The activations vector of the n+1th layer is equal to the activation function applied to the product of the weight matrix and the nth layer neurons added to the bias. The output of our neural network is a scalar and can be written in the form above, where w sub y, l sub n are vectors, and b sub y is a scalar. The cost has already been described previously, but just to refresh your memory, it is half of the square of the difference between the neural network's prediction and the desired output. Gradient descent works by reducing each weight and bias in the model by a factor proportional to the partial derivative of the cost with respect to that weight or bias, in an attempt to minimize the total cost. However, this procedure can also be done with the weight matrices and bias vectors. As you should have remembered from your calculus course, the chain rule can be used. However, for vector value function, there's an extra catch to the chain rule. Since the matrix multiplication is not commutative, the order of the chain rule is always as follows, and never the other way around. Another thing I must introduce before calculating the partial derivatives with respect to the weights and biases in our neural network is the Hadamard product, which is also known as the element-wise product. This operation multiplies each element of a vector or matrix by the same element in another matrix or vector with the same dimensions. The example is as follows. As you can see, for instance, the first entry in the result is equal to the product of the first entry in the first two matrices. This is a useful operation in many different AI models, including deep neural network, but also LSTM and other architectures. With the assumptions and definitions from the previous slides, you can compute the following partial derivatives. The two partial derivatives on the right are the most important because they will be what we are going to use to train our neural network. With the new light of linear algebra on gradient descent, in order to execute it, all we need to do is we need to subtract the partial derivative of the cost with each bias vector from the bias vector, and subtract the partial derivative of each weight matrix from the weight matrix. Of course, scaled by the learning rate. And we could do that for each training instance. Applying this product repeatedly will allow us to do each epoch of training, ideally until a local minima is reached and the neural network is trained. After we have learned the mathematics required to implement the neural network model, we must implement it into code in order to run it and test it. With this, we must use some basic libraries. For instance, the system library in C# is used to print lines, collect inputs, and other related tasks. The Yahoo API library is used to acquire a large quantity of stock data from an online service called Yahoo Finance. And NumSharp and linear algebra library allow us to generate random numbers, for example, in order to randomize the weight matrices at the beginning. As described previously, a specified learning rate and the number of nodes in each hidden layer must be defined before the neural network is created. This is done on line 20 to line 24. On line 27, we started with 200 epochs of training, and more training can be added by the user if necessary in this program. Our training data will be Apple stock data from January 1st to June 30th, 2019. That is acquired from line 39 to line 53. And our test data, which is data the program has never seen before during training, is Apple stock data between July 1st, 2019 and September 30, 2019. And this is done on line 55 to 63. On line 35 and 36 of our program, we made reference to the training instance class. The training instance class is used to create the training instance object, which will contain all the information about our training data. This includes the actual price of the stock, the inputs, which is the previous price of the previous 16 days, the Tinker symbol, which is AAPL for Apple, and the date of which the price actually occurred. The next thing our program does is to initialize our training instances. The list of training instances is initialized from data from Yahoo Finance for both the training data and the test data. Initially, we decided to use high, low, and open prices to feed into our neural network. However, we decided to only use highs for this project to avoid introducing additional confounding variables that may affect our results. Next, we create our deep neural network object, which is an array of 5 layers. These 5 layers contain 1 input layer, 3 hidden layer, and 1 output layer. The output of a given layer becomes the input of the subsequent layer. All of the layers are described by the layer class. The layers class is arguably the most important class in the entire project. It forms as the basis of the neural network. This class is used to create the layer object, which consists of an output vector, an input vector, a weight matrix, and a bias vector. When a new layer is created, the weights are randomized with a Gaussian distribution, while the biases are all set to the 0 vector. The other functions in the class are also crucial to the functionality of the neural network. The update input function updates the input of a layer, which is used in training and testing. The feed-forward method calculates the output from the weight, biases, and inputs, which allows the neural network to make predictions. The output layer class creates the output layer, which is basically the same as a layer. However, it creates a single output as a scalar. It also neglects the radial activation function to allow for continuous derivative, although this is just to make life simpler and does not affect the neural network in any way. After the neural network is created, we must train the neural network. The orange text just writes our data to a file which can be analyzed later. Starting from the beginning, line 128 is where everything happens. Line 129 to 134 implements a failsafe that prevents the cost from increasing due to the exploding gradient problem, which will be discussed later. Line 136 to 139 allows the user to continue training the neural network after the default amount of epochs, as well as reduce the learning rate if necessary. The rest of the code outputs the stock prediction of the trained neural network for both the training data and the test data. The most important part of the training process is the gradient descent, because that is how neural networks train. Our implementation of gradient descent begins with initializing several dummy parameters. These will be modified with every training instance, which will be used to change the weight and biases at the end of the epoch in order to train the neural network. The next lines in our gradient descent function computes the gradient of the final hidden layer, as it involves different computation involving scalars. Then the gradients of the subsequent hidden layers are computed in a backwards order using matrix vector operations and a chain rule. The order of the computation allows some of the values to be reused, also known as the dead horse principle, therefore saving computing resources. This is the reason for the name backpropagation. Next, from lines 327 to 332, the changes calculated for the weights and biases are accumulated and scaled by the learning rate and added to one of the dummy variables. Then the neural network is updated with the next training instance, and this process repeats until all training instances are evaluated for this epoch. At the end of each training epoch, the weights and biases are modified by the appropriate amounts determined by the gradient descent.
With our AI, we tested with multiple learning rates and hidden layer nodes to see how changing these values are going to impact the final results. We did all combinations of learning rate and number of hidden layer nodes except for having 10 to the negative 10 as learning rate and 64 hidden nodes. That means we have a total of 8 results available for sharing, and the graphs for the final output will be presented in future slides. Since our initial values are randomized, we ran multiple tests with each combination to see if we can reach the smallest cost value. For neural networks with 16 hidden nodes, we ran 40 times, 32 hidden nodes 30 times, and 64 hidden nodes 10 times. The decrease in the number of times we ran is due to the increasing intensity of each trial. Increasing hidden nodes will place a heavy burden on the computer running the code, making it many times slower. As you can see, jumping from 16 hidden nodes to 64 hidden nodes increased the time required for it to run by 10 times. Here is an example of the values of the weights, bias, and activation of one neural network. Note that the activation values are the value for the hidden nodes. Hypothetically speaking, the absolute value of the weights and activation will show how relevant the information is to the final output. Values that are close to 0 shows that the data is less relevant, and the data that are farther are more relevant. Here are some data we collected, and we graphed epoch to cost, where x-axis represents the epoch and y represents the cost value. The graph is a collection of all trials with the same number of hidden nodes per layer and learning rates. Most trials generally follow the same pattern, with it being high cost initially and decrease to a relatively low value. However, there are a few exceptions. Looking at the third graph, we see there is one trial where the cost shoots way up, comes back down, and shoots back up again. We theorize the reason it happened is due to too high of a learning rate. The phenomenon is called exploding gradient, where because the learning rate is too high, the adjustment overshoot the minimum value and reach a point in the graph where it's too steep. And since the adjustment is the product of the gradients and the learning rate, it will constantly overshoot and eventually explode, hence exploding gradients. Another data that appears interesting is one of the trial in the second graph, where the cost constantly stays at a relatively high value. This is because the cost function may contain multiple minimum value. Gradient descent will always land in the closest minimum value it started off with. Therefore, it's not guaranteed that it will land in global minimum, and the local minimum value it eventually landed in is relatively higher compared to the rest. The same theory can be applied to the trial in the first graph, where the cost value hovers at a relatively high value.
As you can see from the data, the more nodes in each hidden layer are present, the training requires less epochs to reach the lower costs. This makes sense as there are more degrees of freedom for the neural network model to fit the data. However, more nodes may not always necessarily be good, as it presents other potential issues.
As can be seen here, the neural network with many nodes can predict the training data quite precisely. However, when faced with data it has not seen before, the accuracy can be compromised due to the model fitting to the specific set of training data too much. The middle graph shows a simpler example, where noisy data is fitted to both a linear function and a polynomial function. Though the polynomial function fits the data perfectly, the linear function is expected to make more general predictions and would not lose significant accuracy upon extrapolation. For deep neural networks with many neurons, overfitting can be an issue due to the large number of free parameters. This can be countered using a process known as pruning, in which nodes whose activations do not contribute greatly towards the output are removed. Now we will focus on some of the possible future improvements. For our neural network implementation, we have used standard ReLU since it is easy to implement and has been proven to be effective in the majority of cases. But ReLU can still occasionally run into a certain problem, known as vanishing gradient. Specifically, there are certain situations in which the input to the ReLU function becomes negative for almost any range of inputs. This can happen if a weight becomes too negative as a result of setting the learning rate too high, or if a bias is too negative. As can be seen in the graph, ReLU always returns 0 for negative inputs, and so the node becomes completely inactive for all future training cycles. This is known as dying ReLU. A number of other activation functions that mitigate this problem can be used instead, such as leaky ReLU, parametric ReLU, noisy ReLU, ELU, and SoftPlus. Due to the large amount of stock data that was used for training, we were not able to normalize our input data. Normalization refers to the scaling of all input data to the same range. The graphs in the figure below show the importance of normalization using examples in 2 dimensions. In the first graph, the data is not normalized, and the path taken by the training, shown by the red line, takes many steps to reach the local minimum, since the negative gradient does not point in the correct direction. Normalized data is given in the second graph, and training takes far fewer steps. In terms of the neural network, using normalized data for input allows for all weights to be updated at approximately the same rate, leading to faster convergence. Furthermore, keeping all inputs in the same range allows for more generalizable results, since it is the relative differences between the inputs which are more important than the magnitudes of the inputs themselves. There exist more complicated models to predict sequential data such as stock prices. The most basic of these is the recurrent neural network, which is essentially a feed-forward neural network where the outputs also feed into the inputs. The majority of these more complex models are trained through backpropagation through time. One final goal for future projects is to use a more sophisticated neural network architecture, such as long short-term memory, or LSTM for short. The characteristic feature of LSTM is its capability of storing information in memory cells, which allows it to handle not only single data points but also continuous streams of input. LSTMs can also be trained more efficiently than RNNs since they require fewer matrix operations, and they completely solve all gradient problems present in other neural network models.
My biggest takeaway from the project is realizing that a great way of getting rid of my fear for something is to understand it. It is not uncommon that we find articles online talking about how AI will destroy humanity, or movies about how robots will take over the world. But after this project, I understand that AI is no more than a mathematical model that learns using calculus, which is not scary at all.
For me, the greatest takeaway was to experience all of the ups and downs of undertaking such a large and complex project. Every single task was like a small puzzle to be solved, each one leading towards the next. How is the math supposed to work out? How do we implement this function? Why is the program not behaving as expected? To chase down all of the necessary steps, and finally piece together the whole of the neural network was the most satisfying conclusion to our capstone. And I feel that I've developed many problem-solving skills in the process, which will most certainly play a role in tackling other major projects in my future career.
Let me try again. My final takeaway from this project is I understood what it means to be able to implement something from scratch. Perhaps one might think one understands something when one can briefly understand another's explanation. Perhaps one might think one understands something when one can read and understand what others have created. Perhaps one might think one understands something when one is able to solve example problems. Or perhaps one might think one understands something when one can apply the knowledge to solve similar but desperate problems. I have been through all the stages for many concepts at various stages of my life. The one with the neural network began in ninth grade when I first heard the concept in use. As a curious individual, I began to study the concept on and off whenever I feel like it. I have made two great leaps before reaching the stage I am at right now. One day on the mountain in 10th grade, I realized the implication of the linearity present in the neural network and its impact on the training process. Then another day, the next year at Eric's house, I was able to figure out how the linear algebra and matrix vector operations are used to implement neural networks and how their partial derivatives can be calculated easily. Although these big leaps are important, it has been a long and hard grind over the years, with many nights I left unable to sleep. For this project, we have stepped over many hurdles for both mathematics and programming to accomplish that what we have accomplished. Although I will admit that our deep neural network is far from perfect, it has shown a proof of concept. At the beginning of this message, I say 4 different levels of understanding one may have. However, I believe true understanding is when one can implement given concept from its bare naked components. Once one has reached a stage, one is near immune to deceptions and one gains the ability to logically reason in a certain area. This project for me is more about learning and understanding a concept at this level than minor implications, details, or semicolons. It has been a struggle for many years, although now I can say I truly understand the neural network at least. But there is still much to learn. Understanding something just opens the door to novel ideas. Apart from deep neural networks, I have similar experience with quantum mechanics where I started with many myths that are taught in introductory science course in high school. And again, as a curious individual, I don't like accepting things that does not make sense. While this endeavor is just as strenuous as that of the deep neural network, with countless nights of me being depressed as I was unable to solve small problems, I was able to progress from understanding of cats in 8th grade to deriving the uncertainty relation of the Schrodinger equation, scattering, etc. Soon I will want to be able to solve the bound state of the hydrogen atom, although I believe that I am only on the third stage of understanding right now. As Mozart once said, go on a journey, find countless moments where being lost is the same as being found. Turn the world upside down and let your life live throughout your footsteps.